Okay, thanks. And I thank the organizers for giving me a chance to talk about this in this workshop here. So I want to present a simple result, which is different proof of parallel repetition in a special case, in the case of no signaling games and the kind of multiplayer games that we saw in Ankit's talk on Monday. But the technique that underlies the proof is, I think, interesting, and it's based on a class of theorems that I would call Finetti theorems or Finetti reductions that I'm assuming maybe not everyone or most of you are not familiar with. So I'm hoping, because the talk will be in two parts. I mean, first part will be introducing these Finetti theorems, what they are and what they say, and second part will be, well, how do you apply these to this particular case of parallel repetition. So Finetti theorems, they're just theorems about the structure of distributions that are invariant under permutations of the coordinates. So you fix a finite alphabet, you can think of A as just being 0, 1 bits, and then you take a distribution on strings over that alphabet. And the assumption that will hold throughout the talk is that this distribution is invariant under permutations of the coordinates. And the question is, what kind of interesting things can we say about such distributions? So some examples, for instance, if you take a distribution that's just IID copies of the same distribution, then this is permutation invariant. But that's not the only thing. Another example of a distribution that's permutation invariant, if you take the uniform distribution over n-bit strings that have exactly n over 2 ones, n over 2 zeros. So that's also permutation invariant. More generally, actually, you can convince yourself easily that any distribution that's permutation invariant is going to be a convex combination of distributions that are uniform over all strings that have a certain type, where in the case where my alphabet is 0, 1, the type is just the number of ones. If the alphabet is bigger, you just count the number of times any symbol appears. So that's exactly the kind of distributions we're looking at. And definitely in the 60s, the Italian mathematician showed the following. So he showed that if you have a distribution P, such as this one here, which is not only permutation invariant, but also it arises as the marginal of a permutation invariant distribution P hat on not only n, but also n plus 1, n plus 2, n plus 3, etc., all the way to infinity, then your distribution, you can write it as a convex combination of IID distributions.
So that's the 30s.
Oh, 30s? Did I get this wrong?
Yeah, it's 31 and 37, the two papers.
Okay, I don't know why I said 69 then. Is there something in 69?
100 minus 30.
All right. So 30s, even earlier then. Right. So he was interested. Definitely, I think there is debates about Bayesianism and frequentism, and he was interested in settling that debate. So it's sort of a foundational question whether you can, in which cases can you legitimately assign priors? Like when is it that there exists an underlying prior? And so here you're thinking of drawing random variables. Drawing samples from a sequence of random variables, and you're making the assumption that the underlying distribution is permutation invariant because these samples you don't distinguish, the first sample from the second sample, and then under that assumption there exists a underlying prior, which is this measure dq here that you can estimate just by taking the limits of the frequencies. So it's a whole debate, and so but as far as I know, then nothing much happened on this, and then this was picked up by.
That then P is just IID samples from some.
It's a convex combination, so it means that how do you take a sample from P? First, you take a distribution. You choose a distribution Q, just on A, on a single copy of the alphabet, according to some measure dq. So the statement is there exists a measure dq on distributions on A, such that P is a convex combination according to that measure of IID.
Convex combination of IID.
So how do you sample from P?
So
First,
the coordinates are not independent, but the only correlation is which element of the convex combination.
Right. So they're definitely not right. Yeah. So for instance, you could imagine that P is an example in bit strings, right? Is first you choose a bias for the coin, and then you flip IID coins with that bias. But the dq would be the measure under which you choose the bias in the first place. Because that distribution is permutation invariant, but it's not IID, right? If you do, you choose either bias or quarter or 3/4, for instance.
Is it hard to prove this thing?
No. So I'm going to give you a hint of the proof of something stronger than that. No, I don't know definitely. I don't think he proved it. People didn't prove stuff in that, so he probably claimed it. I don't know if there might be a very easy proof. I'll show you an easy proof, and there might be a. So the easy proof will be of a slightly stronger statement, which was so this was picked up by Diaconis, and then there's a paper by Diaconis and Friedman, where they asked, well, what can you do if you don't make this assumption that you're representable as the marginal of something like. Where r goes to infinity for every r. What if you fix and you just know that p is the distribution? So p is my p hat over there. So p is the distribution on n plus r coordinates. And what I'm comparing is I marginalize over r of the coordinates, any r, the last r, because it's permutation invariant. And I look at the resulting distribution on n coordinates. And I ask, okay, how close is that to a convex combination of IID things in the total variation distance? And so what they showed is that this distance is going to be at most, maybe look at the second term here, it scales like, get rid of the n, so it scales like, did I get this wrong? And right, you should see this as scaling like n over r, right? So n is the number of systems you keep, the number of coordinates you keep, and r is the n plus r is the total that you had. So if you want this error to be small, if you start with something that has 100 coordinates and you keep only 25, this will be like a quarter or things like that.
So this is minimum over Q?
The right-hand side, you mean? There exists. Did I forget? No, there is a measure dq. Yeah, so the best measure dq will do that. Yeah, you can. It's constructive. You can define what is dq. Is it not correct?
That's bigger than 1.
No, so r goes to infinity here. So you think of r as being a large parameter.
It is fixed and now it goes.
Oh, sorry, I didn't quantify everything. But this is for any r this holds.
But we are thinking of this with n fixed and downside.
Yes. So n is the number of coordinates you're looking at. It's this distribution p that's permutation over invariant. But you're adding some extra assumptions, which is that it actually arises as the marginal of something that's permutation invariant on more coordinates, n plus r.
Is there any explanation for these two terms?
Yeah, so I'm going to show you on the next slide. So, well, to some extent, but I think you're going to see it. I can't see it exactly where the terms, but let me show you. So that's the same theorem here. So let's do it for bit strings, just because it's easier. So we already said this, right? So anything that's permutation invariant is going to be a mixture of uniform over strings that have 0 1s, 1 1, 2 1s, etc. And there's definitely such distributions that are very far from IID. For instance, if I take myself to be uniform over strings that have n plus r over 2, so half ones, then this is definitely not IID because it has no variance at all in the numbers of zeros and ones. So if I try to do this as a coin flips, I'm not going to get there. So now, but let's think of what's, but here I didn't marginalize anything, right? So I have to marginalize over the r coordinates. This is what's going to save us. So I'm going to describe an experiment that's going to explain what's happening here. This is the Diaconis-Friedman, what they showed. So what my initial distribution, this permutation invariant distribution is, I can think of it, so let's just fix this particular example when I have half ones. So it's like being uniform distribution over an urn that has half white balls and half red balls, right? Half ones and half zeros. And now, what's the distribution that's obtained by marginalizing r coordinates? It means I only look at n coordinates, so I take n samples from this urn without replacement. And that's a sample from my p in this particular case, right? I started from something uniform over bit strings that have half ones and half zeros. This is this. But now I take only n samples because I marginalized the r extra ones. So this is what I have. Now what would something be that's IID? Well, it would be almost the same, but an IID distribution would be taking n balls from the urn, but now with replacement. If I do that, then all my samples are independent. I'm putting it back in. This is just, in that particular case, this would just be coin flips with bias a half that it would be doing. And so the whole question is just, what is the difference between these two distributions? That's what we're trying to measure as r goes to infinity. And you can imagine that as r is very large, if I take only a small n number of samples, with or without replacement is going to be the same, right? And so these two distributions, the distribution that you get with replacement, this is just Bernoulli coin flips, and the one without replacement, this is the hypergeometric distribution. And so then it all boils down to calculating the statistical, the parameters are just what they need to be, the statistical distance between these two distributions, and you see that it scales like something like this. When they're bit strings, larger alphabets, you get a dependence on the alphabet size. So you can do an exact calculation, and these are the worst cases. Like what's the worst distribution in terms of what's the worst p? It's this. It's uniform over bit strings that have half ones. So it's a very nice, I find it a very nice. So by taking the limit for R, sorry, who was asking for a proof for? Anup, you were asking. So if you take R to infinity, you get a proof of the exact statement, of course. But maybe there's a much easier proof in the case where you know that R can be made arbitrarily large. So for the application I have in mind to parallel repetition, we're going to look at a different formulation of this theorem, very similar, and it's going to apply not to just distributions on bit strings, but what I call systems, so families of distributions that are going to represent the strategies of the players in these games. So now I have two finite sets, my questions and my answers, or my inputs and outputs. And what I look at is these conditional distributions. So this is just notation for saying that I have a family of distributions on this set A, parameterized by elements Q of my set Q. And you can keep A be 0, 1 and Q be 0, 1 for the whole talk if you want. And so now the generalization of the notion of being permutation invariant, I'll call it N exchangeable. So it means that if you permute the inputs according to any permutation, and you permute the outputs according to the same permutation, then your whole family of distributions is unchanged. And here's a different formulation so this is another type of definite theorem from which you can derive the one that I was showing you before, but that's the one that's going to be more useful for us. So take any distribution like this. Then again, there is a measure dq. So the differences are that here I'm not marginalizing over anything, right? I'm taking the original system here. But now I don't have a bound on total variation distance. I have an upper bound. So what this means is that I think I have it below, I'm sorry. So one way to parse this is to say that for any event, E, and you can fix inputs here, the probability that this exchangeable distribution assigns to the event E is at most what? A prefactor, think of this as being a constant, times the probability that the IID distribution would assign to the same event. In particular, if this event was a product event, here you'd have the probability of the event under just one single coordinate raised to the n. So you'd have, and this prefactor here is, you should think of it as being polynomial in n, and then it has an exponential dependence on the size of these sets. And that's going to be an issue later on, but I just want to think about constant-sized sets. If there's more symmetries on your family, you can improve this constant a little bit, but that's not going to be relevant for the talk. And if you know that this result holds, I said it before, by marginalizing some coordinates, you can arrive at a bound very similar to the total variation distance kind of bound that we had in the previous slide, but I've never seen this proven anywhere. It's a nice exercise. Try to show it. This implies the other formulation. It's interesting. Yeah.
Could you just mention what kind of additional symmetries you're talking about?
Right. So if local symmetries. So if, for instance, you'd have that you know that for some reason the distribution P is invariant under, say, flipping the value of A1. Right, so it assigns the same weight to the first bit being 0 or the first bit being 1. So some inner symmetries inside A or inside Q that also leave it invariant. Then you can, this is basically the number of degrees of freedom of just one system, like Q times A. And if there's fewer degrees of freedom, you get a better exponent. It's very easy to prove this. This is counting. So before showing you briefly how this can be applied, is this okay? Everyone can parse this, because this is the thing that I'm going to use.
The joint distribution of AN and QN doesn't need to be exchangeable, right? Otherwise, it would be, I think, a result of the Finetti norm. The joint distribution of...
No, right. So this is a more restricted... if you thought of this as just a distribution on, A cross Q repeated n times, then it wouldn't be exchangeable across, yeah. So there's a few applications of this. There's many more applications of this. Okay, so so the original theorem, it's been generalized to Markov chains. So where the assumption of permutation invariance is a bit weaker, it's a Markov chain-like kind of assumption. It's been used to study graph, but I don't know much. Also, there's some free probability. I don't know much about these. Something maybe closer is, so Jairam has a paper recently, very nice, sort of generalizing this notion, so studying it under weaker assumptions than the full permutation invariance, and so proving results related to that, and then they have an application to analyzing rounding algorithms. But aside from that, it hasn't been that much used in theoretical computer science, as far as I know, except in quantum information, where it's a very important result. So there's generalizations of this that apply not to classical distribution, but to quantum states. So saying that these quantum states, density matrices, are invariant under permutation of different systems. And the theorem in that case says that those states are close to separable. It doesn't matter if you don't understand that. But it's used in many different contexts. For instance, showing security of quantum key distribution, or showing that certain methods for performing tomography are particularly efficient. It also has applications in Hamiltonian complexity. So there it takes on like many different flavors that I'm not going to touch upon. So let's move to applying this to the setting of parallel repetition now. So let me just briefly recall the kind of games that we're thinking about. So same kind as Ankit's talk on Monday. There's going to be K players, think of K being 2 or 3 or 4, that interact with the referee. The referee chooses a tuple of questions, sends them to the players provide answers, and then the referee decides to accept the answers or not, depending on the questions. And all this information is public. There's a distribution on questions that I forgot to write down. So what's a strategy for the players in a multiplayer game? In general, it's just a function, right? From questions to answers. And to be fully general, we think of these players as acting jointly. So they have a joint strategy, and this joint strategy goes from the whole K tuple of questions to the whole K tuple of answers. And so this is described by a family of distributions like this. And so the game, you can think of it as acting as a linear function on this set of strategies. And so I define the value of the game to be the maximum success probability of any strategy in the game. This is just notation. Here, what do we have here? Supremum over all strategies, all allowed strategies. This is what my F will be. Of the average over the choice of a random question, according to some distribution, I sum over all answers. I count 0 or 1, depending if the answer was valid or not. And this is the probability of my players actually giving me the corresponding answer. Simple expression. And so then you can study this value under different restrictions on the players. The typical restriction is that what I would call the classical restriction is these players are classical. What kind of strategies can classical players implement? Maybe using shared randomness, convex combinations of product strategies, right? So this is thinking each of them just using a private coin. And then if they also have a public coin, then you get the convex hull of such product distributions. But you can look at other families of players. For instance, quantum players, the kind of distributions that they can implement would look like this. It doesn't matter, I'm just giving you. The one that I was going to look at in the talk are no signaling strategies. So this is sort of important, just the definition. What's a no signaling strategy? It's something that might lie outside of this convex hull. But the restriction is that if you look at the outputs, the answers, you marginalize and you look only at the outputs on the subset, then this distribution only depends on the corresponding inputs, right? So if I look at only the answers in the set T, but I change the inputs or the questions outside of T, so to other players, then the marginal distribution is unchanged. So that's no signaling strategies. Maybe a quick example. So if you take, bits, 2 players, bits, these are my questions and answer sets. Let's take the distribution that's uniform on all pairs of bits, A1 and A2, whose parity is 1 if both questions were 1, and whose parity is 1 if both questions were 1, so they're different, and whose parity is 0 in all other cases. Then this is no signaling. Why is it no signaling? Because the marginal distribution on either side is uniform. You can check that because I'm always taking the uniform distribution over all pairs of bits that have a certain parity. And so the marginals are uniform. So it's definitely no signaling. But you can't write it. It doesn't fall in this convex hull. It doesn't even fall in this set. So then, there's no signaling distributions that are not classical or quantum. All right, and the question that we want to study is that of parallel repetition. We saw that on Monday. How does the value of the game repeated n times relate to the value of the original game? And so here you could say, what is the amortized value of the game under parallel repetitions as the number of repetition goes to infinity? So I'm just playing this game n times in parallel and accepting the answers if and only if they were correct in each repetition, in each instance of the game. And so I had a survey of known results, but it doesn't, maybe this doesn't really matter too much. Because I don't have so much time. So let me just try to say a little bit how you'd apply the Finetti theorem to study this question in the no signaling case. All right. So, I mean, the point is that why would you hope that parallel repetition holds? This verifier, you're running the game. These are n instances that are played independently by the verifier. So what's important for that is that then we'd like to claim that the best that the players can do is also play independently because of that. So we know that doesn't hold in general. What we do know though is because the referee treats all these repetitions independently, we can assume that there's some permutation invariance on the strategy of the players because the referee could permute the questions at random, get the answers, undo the permutation, the result would be exactly the same. So this is the one element of structure that I have on the strategies of players in a repeated game. It's the only thing that I know. It has this permutation invariance. And this is good because this is exactly what we want to be talking about. This is the same expression for the value of the game. I rewrote the Finetti theorem there on the top. We want to be applying this. This is something that applies to permutation invariant distributions. We have a permutation invariant distribution. Let's apply it, right? So the value of the game is a linear function of that distribution. All the coefficients are positive. So the inequality, I can apply it. It goes through. And I get this. And now what did I do here? I used the fact that this criterion for acceptance in the game, the repeated game, is the product of accepting. You accept here, this is 1 if and only if you accept it everywhere, so it's the product of the things. This, once I've upper bounded by this, it's also a product. So what I get is this expression there raised to the nth power. So this is quite nice because now I recognize here just the value of a single instance of the game. When the players would play the certain strategy S here, that's given by my measure, my sort of prior on strategies for a single game. And so, all right, let's raise this to the power 1 over n. We get this constant to the 1 over n, so this is going to go to 1 as n goes to infinity. And then this here, I can just take what's the worst case, right? So I'll take the supremum over all strategies in the support of my prior of how well that strategy does. And this will be raised to the n. When I raise to the 1 over n, I get the value of the game. So I've sort of proved parallel repetition for you. I have that the amortized value is at most something that goes to 1 times the best that the strategy could do in the single game. So it's the issue here. The issue is that I don't have control over the support of this prior distribution here. So this Finetti theorem is saying that there's a prior. This prior is a prior over strategies for the single game. But what kind of strategies? Are these classical strategies, quantum strategies, no signaling strategies? I don't know. Could be anything. Could be, this is just a function from tuples of inputs to tuples of outputs. If you want to implement it, think of it as a strategy. It might require a lot of communication. And it's easy to see that this can happen. In general, you can have a very nice distribution that's no signaling anything you want, for instance, the uniform distribution. And you can write it as a convex combination of things that are very wild, right? And so here, I'm taking the supremum over very wild things of how well they can do in my game. So this could be just 1, and then I haven't achieved anything. So this is why you sort of want to apply that theorem, but it's not trivial to apply it. And I should say that actually we have counterexamples to parallel repetition or certain ranges of parameters that show you that you can't just hope this outline to go through just like this. And I should, how much time do I have? 5 minutes, 4 minutes, okay. So then the work is to go around this, and this is what we did in the no signaling case, and I don't know how to do in the classical case. So I guess I get to say a few words about this. So the point is now we have additional structure on this S. There's this no signaling condition. And we want to find a way to say that such a condition should hold also on these strategies S that show up in the support of my prior, or at least in those that show up with non-negligible probability. And so the outline of the argument is this. Well, suppose that we start with something honest, so a no-stealing strategy for the players, and we'd like to argue that this measure here doesn't place too much mass, not much more. We're shooting for exponential decay in these success probabilities, so we're shooting for really small mass on things that we cannot control. And the reasoning is by contradiction. Suppose for simplicity here, let's assume this was an equality, right? So suppose I wrote my no-signaling thing as a convex combination of things that are IID, but some of them might involve signaling. They're not strategies. I want to rule that out. I want to say there should be few of those. And so the argument will say, well, if there's really a good chance, or a non-negligible chance for this prior to be signaling, then this thing here should be signaling. And that will use the fact that I have n IID copies. So it's sort of, yeah. And so the idea is to say, to try to implement this, is to say that suppose this was the case, and suppose I was to give the ways possibility for players to sample, use this distribution as some kind of a distributed resource, then they could signal using this, and then we contradict the assumption that it's no signaling. And how would they signal? The idea is that maybe I don't know if it's so useful to read what I wrote here. The idea would be just look at this. You get a sample from this, right? So which means first you choose a sample S from the prior, and then you get many IID copies. And you know that there's a small, because we're reasoning by contradiction, you know that there's a small chance that the prior selected some distribution that was signaling. And so what you can do is you can try to observe, do some kind of tomography, do some statistics on a subset of the coordinates, using that determined what kind of distribution did you have. If it's not a signaling distribution, then you sort of ignore it, do nothing. But if it is signaling, then you can use the remaining coordinates and the sort of signaling power that you have in these remaining coordinates in order to signal. So in order to exchange information between the different players in the game, and this will contradict the original assumption. And the difficulty in doing this is, and this is why we can work it out in the no signaling case and not in the classical case, is how do you estimate this distribution that which element of the prior, the IID sample that you get from was given to you? Because you need to do that as separate isolated players. And so if you're just trying to distinguish whether the prior selected something that was signaling or not, then this is easy to do locally without any communication. But detecting whether you were given something that's classical or not, quantum or not, this is not something that I know how to implement locally, and this is why the thing would not extend. And I'm going a little bit fast because I'm out of time. I think this was a little bit more details how this is done, but I guess I just gave you the outline. This is a repetition of the outline. Maybe I just state the result and then I'll end here. Here's the result, and there's some, I just want to point out, the kind of advantages and drawbacks it might have. An important advantage is that it extends almost as is to any number of players. Number of players is not so much important here in the no-slinging case, and having parallel repetition for games with more than 2 players in the classical or quantum case, this is a challenge. So this might give you some idea that this could be interesting. Another interesting thing about it is that it very easily gives you threshold theorems instead of just parallel repetition, just by the exact same arguments. And it gives you a threshold theorem with optimal sort of concentration around the expected number of repetitions that you should satisfy. The bad thing about the result is this prefactor. And in particular, the fact that this is polynomial in the number of repetitions, but there was this exponential dependence on the number of questions and answers. And this is really due to the Finetti and also this method of doing statistics, estimating what element you got from the prior. If you want to be able to do that reliably, you need at least as many samples as the support of your distribution, and that's the number of questions and answers. So it seems that this kind of approach is limited to having very bad exponential dependence on these question and answer sets, which means it's not going to be useful, for instance, for hardness amplification or such things. So it has advantages, it has drawbacks, and I'm over time. I apologize for that. Let's stop here.
A quick question or the next speaker sets up. So when it is for the K player space, you are saying that it's for the complete set.
Yeah. Yeah, so it's very interesting, but no signaling strategies that do not have complete support are very strange. In particular, you can have something that it depends. It ends up depending how you define non-signaling. So you can have strategies that sort of distributions are non-signaling for the questions on which they're defined, but it's impossible to extend them to something that's globally non-signaling, and that creates a problem. It's related to the parameters. So if you you need to do all these up to some error, and then you need to say what's something that's approximately signaling, and say that something that's that's close to non-signaling is going to not have a too much larger value in the game than something that's exactly signaling, and that's where things start breaking down if you don't.
Okay, let's try to call this again.